Okay, so and now for something completely different or somewhat different. So a bit about myself. I come from the Haskell programming languages world, and I'm a maintainer of the Haskell package repository, and do work on the Cabal package manager for Haskell. But this talk is not about them directly. They are really cool. There's cool articles and blog posts about them, written largely by well-typed, a neat TUF implementation, really interesting, lazy algebraic solver, good stuff. I'm not here to talk to you about that. I'm talking about sort of some broader theoretical work I started doing the more I got involved into sort of being concerned about the ecosystem and all of this stuff as a whole and how it fit together that in theory, should help us think about solvers and also just about what it means to maintain package repositories. So it's one thing to solve whatever problems you're given. It's another to sort of state the universe of packages in a package repository and think about how one could manage that and update that so that it's a better landscape for solvers and users both. So one thing Hackage has is metadata revisions that let you sort of bump bounds after the fact of publishing a package as new information comes in. And the ideas in this talk came out of that. They're at this point, it's sort of a formal, right? I'm a programming languages and semantics background, so I wanted to apply those tools to try to think about package repositories mathematically and hopefully set some foundations for people to think about and work about more engineering-oriented applications. This talk is an advertisement for. There's no way it can go through a fraction of the material in two papers that I've worked on that are up on archive. I'm going to paste them in the element room right now. That's one, and let's see, other. Okay, and now let's come back to talking. So I mean, naively, one starts out thinking about a package repository as, it's a bag of packages, and they got, there's a name and number, and it's just an indexed, set of bundles of code or whatever. And I'm here to say it's not that at all. It's got a lot of hierarchy and structure if you try to map the thing as a whole, versions and ordering. Dependencies can be on version ranges, so you have a full logical language of expressions, and also conflicts, all things we've been talking about. Those are not, I would say, those are part of the structure of the package repository itself, if you want to think about it as a mathematical object. So yes, you have names and packages, but you have all these interrelationships between them, and naturally, as developers, you can see throughout this conference, people have been talking about dependency trees. But when you look at the package repository itself, the dependency tree structure does not suffice to explain what's going on, because the dependency tree doesn't encode all of this sort of version range information and all of this choice and conflict information that's in the metadata of these packages. So what is the structure? And that has that these correspond to. If you want to actually sort of, draw a bunch of, labels and lines between them and whatever, how could you do that to actually fully capture all the data in a package repository in a meaningful way? And I'm going to try to walk you through at least that element of this work. Again, it's not a bag of packages. So the atomic elements, if you want to think about, atomizing things, smash them up until the constituents, it's not going to be a package. And here's a simple example of why. Package B depends on package A. So you can subtract, B from the set of packages BA and get A. Great. But you can't go the other way because B doesn't exist without A. It depends on A. So these are not individual atoms that you can sort of combine and recombine and union and intersection as sets in a comfortable way. So we're going to say, well, maybe it's just a package set, so that, now you can say the package set BA, but you just can't say the package set B. And now that one way that one can think about that will say that, okay, now we're and then if you give that an order-theoretic structure, you can say BA minus A, least upper bounds to a unit or something. So that's an idea, but there's still problems, which is conflict, for example. So you have B and C, and they both can't be installed at once. Maybe they're two different versions of the same package. But now you can't union these two gadgets together, B depending on A and C depending on A. That's not meaningful. Or suppose that you can build B depending on A or B depending on D. Then if you merge both of those together and union them, which B do you take? Or do you have two copies of B? So this very natural feeling idea of even moving from packages to package sets isn't rich enough to capture all the logical structure in a package repository and give it sort of a meaningful graph theoretic or lattice theoretic structure. So we're going to, it turned out, and this is this first contribution, is there is an existing body of research on mathematical structures for programming languages that corresponds exactly to what package repositories give you. And when I say package repository, I sort of mean the full search space of information that you're going to be feeding into, say, a solver. And these were developed by Nielsen, Plotkin, and Winskell in the late 70s, early 80s is the first paper on it. And they're called general event structures, or at the time just event structures. And they're triples. And they have E, the set of events, which would be here instead the set of packages. And, with each version of each package, or each flag on each package, then sort of exploding out into a new package, conceptually. D, which is a dependency relation. So each package is going to map to the double power set of all possible packages, which is to say it's a sum of products or an or of and. So that's going to be B can depend on the set A or the set C or the set, DE. And then we're going to have conflicts, which is either a conflict or a consistency predicate, because you can do it up closed, down closed. And these need not be binary in the general setup. So again, that's going to be simply a double power set. And that's going to be sets of packages that are mutually incompatible. So you might say A, B, and C can't all be installed together. You can have A and B, or B and C, or A and C, but you can't have all three of them together. And now that's going to be required to be there for upward closed. And dependencies likewise have a closure condition, which is transitively closed and cycle free. So these are actually, it's a bit of a mouthful or a mindful to get your head around, but these are very well studied objects, and a lot of work's been done on them, including sort of the relations to Petri nets and other versions of concurrent semantics, and processed especially by Winskell. And you can, when you work out the correspondence, see this is a very full general model of what's happening that's very satisfying. However, it is not an order-theoretic model, which is the model we want to think of in terms of dependency trees and graphs. It's algebraic, rather. This is where some of the work that I did with my collaborator, Ray Posio, comes in. We have an order-theoretic characterization of these general event structures that turns them into much more comfortable gadgets. Given my time constraints, I'm not going to give you a full crash course on order theory. I am going to tell you about just quick review. And again, look at the paper and the citations for more. This is an invitation to it. So recall we have partially ordered sets, and you've got your set, and then you've got your ordering relation. So some elements are ordered with regards to others, and that better be transitive, but elements may be unordered with regards to each other. And that's what we think of when we think of dependency graphs normally. But now we're going to get into some richer bits of order theory. If everything has a least upper bound or a greatest lower bound, that's your join or your meet, and then you have a lattice. And those are very comfortable. Those are what we think of when we think of, sets ordered by inclusion as a partially ordered set, because that's your union and your intersection, or your logical or and. So lattices, and in particular distributive lattices, where or and mutually distribute, will, in the finite case, give you models of intuitionistic logic, which is, so now because you get an implication in that setting, and you've got a full semantics of a logic, right? So this is the stuff I like as a programming languages person. And in itself, it gives you a way, if we had a distributive lattice, we would really have a logic of dependencies in the sense that one would hope. We could throw our logic tools at it very directly. We don't exactly have that. But what we have is gets us close. So without giving you the logical properties that hold, there's things that are a bit weaker than distributive that people are comfortable with, modular lattices, and then semi-modular lattices, which are upper or lower. And I just mean upper by semi-modular right now. And here's some pictures. Again, crash course, sorry. The distributive lattices will look something like this, all photos from Wikipedia. This is M3, one of the canonical non-distributive lattices where and or don't distribute over each other. This is another non-distributive lattice. It doesn't contain M3 as a sublattice. It contains a pentagon buried in here. What's interesting about this gadget is he's semi-modular but not modular. So these are just some pictures of the sorts of diagrams we want to be able to produce to think about package dependencies. And without proving it to you right now, we've got a theorem that says if you take a general event structure, aka a package repository, and then you get a full correspondence to the order-theoretic objects that are upper semi-modular lattices without M3 as a sublattice. Now, I'm not going to walk you through that, but that's a precise isomorphism in both directions. So we've got a full order-theoretic characterization that gives you all the data in a package repository as a graph-like structure, which I would hope people would sort of find useful. This particular class of graph-like structures is a bit odd, but maybe there's things that can be done with the properties of it in particular. When you want to add conflicts, that's in order theory just adding an anti-chain as additional data, which is to say a mutually unordered set of elements. And so here's a very simple example of what you get out. You've got the empty package set. A depends on nothing, B depends on nothing, C depends on A, D depends on B. You can union A and B. You can union A, B, and AC, get ABC, and here's a cut. If you say, well, A and D are mutually incompatible, then you just got to chop off this part because anything above this line is going to include at least one incompatibility. So these are the sorts of structures you get out of it. They're big, but they're good to think with, and they're algebraically very pleasant. It's not a distributive lattice yet, though, on this setup. But we then set out to say, well, we really would like a distributive lattice. So how can we turn the structures that we've got here, these nice order-theoretic structures, into these distributive structures? And we came up with a very nice, surprising result that hopefully will be of interest, which is we rediscovered a semi-lost theorem of McNeely's from way back at the turn of the last century that was then rediscovered again and then forgotten again by Bruns-Laxer in the 70s for the most part. And it's a pure resultant order theory that says that in fact, in the most general statement we have of it, any partially ordered set has a best completion through adding more elements that it embeds into one of these very nice distributive lattices that embody logic in a uniquely best and minimal way. That furthermore is idempotent, so that once you embed it in there, if you apply this operation again, you get back what you started with. So it's a completion or a universal distributive hull or the like, and it's got a very simple construction that we sort of derive. It turns out, following McNeely, it's implicit in McNeely's work that if you have a finite partially ordered set, this completion is the upward closed sets of the join irreducible elements, which is a bit of a mouthful, but the paper walks through it. And if you understand the definitions, it's very simple to state and to calculate. And here's an example of it, where we start with this lattice, which actually looks just like S7, where you have A can depend on B or C, and B and C depend on nothing. And you have this, and this is not a distributive lattice. We're going to apply the Bruns-Laxer or the McNeely construction, the distributive completion to it. And what's going to happen is we're going to get new elements introduced for A depending on B and A depending on C become two different new elements. So that now you get A depending on B, BC, and A depending on C, BC are different. And then that introduces a new top element because you can have both of those A's built both of those different ways. And so what's striking about this is you proceed purely mathematically, order theoretically, using sort of, classical results towards a goal. And what we've got here is we've said, oh, okay, the distributive completion means that you're attaching to each name the full tree of dependencies that were built up to get you to that. And, well, what if we hash that tree? Well, then we would have a Merkle hash. So in a sense, this gives you some of the algebraic properties of Nix that make it pleasant to work with, is that it, in a sense, it atomizes packages by coupling their identifiers fully with their hash that built into them, which means that you recover union and intersection and distribution and set-based logic on top of dependency trees that otherwise are very much not set-based. So hopefully that's an insight for Nix folks or folks that might be interested in Nix. And of course, we know Merkle trees are used in Git and elsewhere as well. About some of the logical properties as well as the engineering properties behind why hitting everything with a Merkle hash makes life good for engineers. So that paper, here's a bit of an advertisement for more, and has a lot more in it. It has a tiny bit of locale theory in it that does more logical work. It studies package version policies, like Semver or Haskell's PVP, which is slightly different, in a certain amount of detail. And it says, what do PVPs do to or contribute to the lattice structure of package repositories? And it turns out logically that they actually amount to adding a modality in the sense of modal logic to package repositories. And for you FP kids out there, that means that in a sense you get a monad for this, which lets you model some logical operations much more efficiently in terms of solving. And it does some actual work in terms of very rough complexity bounds that you can build on top of problems once you've got things in this lattice theoretic setup, because once you've got these trees and whatever, you can enumerate the sizes, the width of the tree, and the maximal search paths and so on, and hit them with some enumerative combinatorics to figure out how you can minimize the entire search space of a package repository as a whole. So it does a little work in that direction. So there's a lot going on in that paper, and I don't have time to give you really even a full preview of the other paper, but I will give you a taste, which is, I told you how you have a semantics of a concurrent programming language and a general event structure, and why that corresponds to, in some sense, all the data in a package repository. Once you have a semantics, you can say, well, why isn't there a syntax for that directly? So what if we tried to create an event process, a calculus, a programming language, whose terms corresponded to package repositories? And that's what this paper does, the second paper. And so inspired by the Pi calculus, it creates a process calculus designed to correspond to package repositories called concurrent exclusionary processes. And here's the intuition, in a way, the high level, about why a package repository would be thought of as a concurrent program at all. Is, well, it's a non-deterministic program where you, the user or whatever, will at each step say, what package can I install next? And then you just type, apt-get that package. And then out of the packages that are now available to install, which is more because some dependencies have been satisfied, pick another one that doesn't conflict with anything and apt-get that. And so, just keep typing apt-get until you get bored or your hard drive fills up. And so that is a concurrent non-deterministic program. And CEP corresponds to that. And so this paper does the things that one would hope from a programming languages paper that introduces a process calculus. Like, it gives you just, here's the reduction rules and whatever. And it introduces some algebraic properties, a nice equivalence relation with bisimulation, which is what one wants from any paper on or any study of a concurrent calculus, and all that usual stuff. And then it throws in a bunch of category theory that tries to give you a category of package repositories and morphisms on them. What does it mean when you merge package repositories? What is a consistent or inconsistent extension of a package repository with new information, or quotienting of a package repository by merging existing packages, and so forth. So again, really just an advertisement. I know it's pretty cross-disciplinary. If you're comfortable with any one of these sort of fields that some of the stuff is drawn from, maybe there's at least one thing there for you. And so I'm hoping here, this is a wonderful conference for people interested in these questions that might want to see, try to fit them both into the, the raw engineering side, but also think about the formal computer science elements of the question as well, which I think are very promising. And it's an invitation to, try to pick up and see where you go with these ideas too, I would say and ask, is that, when I started doing it, it turned out there was a lot of surprises, a lot of really interesting structure that just people hadn't been looking at. And I'm sure I've only scratched the surface along with my collaborator, Ray Puzio. And there's a lot more wonderful results lurking around every corner. So hopefully I've interested you in maybe taking a look yourself at some of that. All right.
I was still muted. Thank you for that. This was super interesting. There's a few interesting questions for you, and we actually do have time for them. So, for starters, what's the meaning of locality in your lattice space, and what's the practical application of it? I'm having a hard time understanding the use of the lattice beyond what you get from just hashing.
I'm not sure I understand this question. I'm sorry. When I say lattice, I mean order-theoretic lattice, right? There's other meanings of the word lattice. So in that sense, I don't know what you mean by locality. That's not an order theory term. You might have noticed when I said the word locale. Locale is not locality. Locale is topological concept. It's a generalized notion of a topological space that's built out of order theory. Steve Vickers has a book, Topology via Logic, about it. So the use of the lattice is that it's an order theoretic structure. It's the graph, and it's got logical properties that let you reason about portions of your entire space of packages and their compatibilities put together.
I believe I'm not the person who asked this, and I believe it was Todd. And I think he meant that more from a global optimization perspective, as we were discussing in an earlier talk, if you might remember.
Yeah. I don't have a theory of optimization on this. That's not what I'm doing. I think there's a basis for developing some ideas. The most important ones all revolve around the idea that about how much can you pre-compute and share between problems by calculating packages in your package repository sort of once and for all, rather than having each solver have to figure this stuff out on its own. Way that I think this might relate to a lot of the prior work would be, it's very important for the ASP standpoint and also from the Rust standpoint with the Dart algorithm, PubGrub, that you have, conflict sets, right? Not only for explanations, but they're what enable fast optimizations. What if you could pre-compute the really common conflict sets ahead of time instead of each time you ran the solver having to rediscover them? And what if when you downloaded the metadata of your repository, it also gave as a hint, here's a bunch of conflict sets to avoid before you even run the solver yourself on your own, little laptop, right? And I think thinking about the package space as a whole is a way that you could try to find that stuff better.
Cool. And it looks like we have time for another question from Paul McKee, which is somewhat interesting. Is the distributive lattice required for SAT solving to succeed?
No, I mean, people are normally sat solving just over the formula that they're given. The distributive lattice isn't about sat solving per se. It's about having an internal, well-behaved logic. If you because basically, if you have a purely distributive lattice, then all of your operations, like if you have a set of packages and another set of packages, and you require both of them, you could just union them and there would never be a problem, right? And if you had so it's, and then you have your distributive laws and all this stuff. So in a sense, what it does is it makes the problem space a lot simpler, and it's not just for raw solvers, but it's also much more human tractable. And I think people that have worked with Nix as just attest to this, right? The more you hash everything uniquely with where it comes from and whatever, the more things you can express and the more things you can say. And because your system doesn't get namespace clashes between things that have the same name but were actually built slightly differently, sort of just, the more things you can that are actually allowed. And I will note that part of this also is this is why I wish there was a talk on Cabal. Ain't my talk. Is Cabal also uses a Nix-like store for hashing and storing all of its packages that it builds in globally, and then it sort of slices out consistent pieces of that for local sandbox package. So in a sense, when you're doing that in the Nix store, what you're doing is you're just instantiating different pieces of this picture I showed you of this global structure. So, but a lot of my work was just.
I'm sorry, but I'm gonna have to cut you off. As much as I find this conversation interesting, we have a time constraint.
Well,
so
sorry, I can go on. I would love to go on. Hit me up in chat. Hit me up by email if you're interested in pursuing this more. You can tell I think this is absolutely fascinating, and that's my big advertisement is if you're interested by this, I will talk your ear off about it, and I will gladly explain these elements. So.
I can tell you that there's a few people in the Element chat who are very interested in having this conversation right now. So you can hop over there and keep this have the conversation there, I guess. See you there. And thank you for the talk.